So a couple days ago, before our experiment, I introduced to you the solubility product constant, which is essentially applying the equilibrium expression law to a dissolving substance. An example that we saw yesterday was calcium hydroxide, right? We started with a calcium hydroxide saturated solution, which then broke down into calcium ions and hydroxide ions, 2 hydroxide ions. And the solubility product expression, concentration of the calcium ions times the concentration of the hydroxide ions to the exponent 2. Again, I mentioned yesterday that I kind of jumped ahead into getting into those very easy to use equations, and I didn't really write down that solubility product expression to any great extent because we really just substitute straight in. But just to go back and look at it, the reason it's called a solubility product is because when we're talking about something dissolving, we only have our aqueous ions, which are all products in the equilibrium expression law, and so it's always one ion times the other ion, maybe to some exponent, which is why we call it a solubility product, because it's always a multiplication of a handful of numbers. We do not include the solid in this particular equilibrium expression because we don't include liquids or solids in any equilibrium expression. That's why it's called a solubility product. So what we did last day was we came up with a handful of general equations that we could apply to calculate the solubility, the molar solubility, how much of this solid is dissolving when we create a saturated solution. All right, and that's what we did on Monday. What I want to talk about now is predicting precipitation. So instead of creating a saturated solution by just letting some stuff dissolve, we're going to be asking the question, if we mix 2 solutions together, or if we have certain ion concentrations in solution, will a precipitate form? All right? And we did this last year, except we did it very qualitatively. We did not use the numbers. Nothing to write down here right now. All right? At this point, I'm just reminding you of the way we would have predicted precipitation last year. Last year when I introduced you to double displacement reactions, which is funny because I just did the double displacement reaction lesson like 2 days ago in the grade 11s. But last year when I taught you about it, and we did the double displacement, and you had to predict whether a solid would form, we guided you to the solubility chart, and if we were looking at, will a precipitate form between lead nitrate and potassium iodide, when we trade the partners around and we check out lead iodide, we get S, and yes, a solid will form. All right? And then you did double displacement reactions and you saw precipitates, and ooh, it was all exciting and fun. What we want to do now is we want to do it quantitatively with numbers. What if we had such dilute solutions of potassium nitrate lead nitrate and potassium iodide? What if they were so dilute that if you mix them together, that a precipitate didn't form, even though we should get lead iodide to form? Because that could be the case. If the concentrations of the ions of lead and iodide are so low, so small, that there's not enough ions to actually get them to stick together and form a solid, then even though we predict a precipitate, it could be that a precipitate doesn't form. So we want to now bring into this a measure of concentration so that we can predict with more detail, with finer detail, whether a precipitate will form or not. All right? So this is grade 11 way to predict a precipitate. Now we're going to be using our KSP values in order to predict precipitation. Okay. You can write this down. Again, square brackets just means molar concentration of the ions. So now in this case, will a precipitate form? It's like we're creating that saturated solution potentially in a beaker. I think I've got that locked, I guess. Yep.
Thanks.
No problem. We're creating that saturated solution, but we're not creating it by a dissolving process, which is what the last lesson was about. The last lesson was, what's the solubility? How much can dissolve? But we're creating that saturated situation by adding the ions from separate sources. So we still need to think about our double displacement situation. Let's trade around the ions, and then let's think about whether one of those is going to potentially form a precipitate, and then we've got to actually do a calculation. And the question becomes, do the concentrations of the ions that we've poured into this new solution fulfill the requirements of the equilibrium expression law? Okay? The questions will go kind of like, will a precipitate form if so many milliliters of calcium nitrate is reacted with so many milliliters of sodium hydroxide? Put them in. You'll calculate the concentration of the ions. You'll put them in the equation. And this question is actually exactly the same as, is it at equilibrium? There it is right there. When you mix the two together, you're really asking the question, is our new solution at equilibrium? Is it perfectly saturated? Is it below equilibrium? Does it not have enough ions in it? Nothing's going to precipitate. Or does it have way too many ions in it that, yes, a precipitate has to form? So again, this question is a perfect example. It's truly an application of, is the system at equilibrium? So we solve it the same way. We will be calculating for a Q. And this time we call it a QSP because we're talking about solubility. And we call it a trial ion product. It's like a test, K. So we calculate it exactly the same way. Again, the equation for Q is exactly the same as the equation for K. we're going to be putting some numbers into it, and then we're going to be making a critical decision. Is it greater than the K? Is it equal to the K, or is it less than the K? Again, to just give us a little reference here, if I had something like A, B, solid, breaking down into A plus, I don't need the square brackets yet, but anyway, A plus aqueous and B minus aqueous, then in this case, we're going to calculate the QSP as being the concentration of A plus times the concentration of B minus, all right? And again, we don't put the solid on the bottom, so really the size of this value is determined by the concentration of the ions. It's only determined by the concentration of the ions. Okay? So essentially, this is concentration of the ions that are in that particular thing. So if the Q is too big, it really tells us everything about the ions. If we do a test calculation and we find the Q is big, it means we have too many ions. There's too many ions in the solution. And if the Q is too small, there's not enough ions. The concentration of the ions is too low. Again, all the interpretations of the Q. If when we calculate this, the Q is smaller than the K, there's not enough ions in the solution. It's not at equilibrium. Now this is a little different than the shifting equilibrium that we learned when we first learned about is it at equilibrium or not. If I'm bringing ions in from a separate source and the Q is less than the K, the equilibrium isn't going to shift anywhere because there is no solid to shift. It's just ions. So if the Q is less than the K after mixing two solutions, it just means that there's not enough ions and we say it's unsaturated. If there was more solid around, it would shift to the right and dissolve more solid. But if there's no solid around, then it's not going to shift anywhere. It's just going to sit there. It's a failed precipitation. We would simply say it's an unsaturated solution. So if we had some solid, it would shift right. But if we're mixing this from two separate sources of, say, calcium and hydroxide, then it simply means there's not enough calcium ions, there's not enough hydroxide ions, there's no solid, nothing's going to dissolve, it's just not going to form a precipitate. So if the concentration of the ions is too low, if it's such a weak solution, even though on our chart it said S, it might not form a precipitate. If the Q is equal to the K, then we have a perfectly saturated solution. That would be quite a coincidence to actually make in a lab a perfectly saturated solution. It would probably be difficult to do to get the concentrations perfect. But theoretically, if the Q is equal to the K, it's perfectly saturated. It's not going to crystallize. There's just the right amount of ions that can be held by that solution. And if the Q is greater than the K, then there's way too many ions in it. Technically, we would have what we would call a supersaturated solution, but once you initiate the crystallization process, it's going to form a precipitate and it will precipitate out. So what we're doing here is simply applying the is it at equilibrium scenario to our solubility problems. Okay, let's do some examples. And these are on your page. And so you can just make reference to it. I believe that's the same question here. Now we're going to start off slowly. This is the easiest of the easy. I'm telling you we're going to have some copper ions and some chloride ions, and we've mixed them into a container such that their concentrations are 4.1 times 10 to the minus 4 moles per liter. So we must have mixed up some copper ions and some chloride ions in such a way that it resulted in the concentration of that copper plus 1 equaling 4.1 times 10 to the minus 4, and the concentration of the chloride being also equal to 4.1 times 10 to the minus 4, and that's moles per liter. And you might be wondering why I'm writing that down like this, and that's because in the more complicated questions, we will be mixing two solutions together. We're going to have to do some dilution calculations. We're going to have to, gather up some information. In this case, I just gave it to you, straightforward. Notice I've given you copper chloride, the KSP. Now, you don't necessarily need an equilibrium equation for this, but I'm going to write it out. This is copper plus Cl minus. These are aqueous. And the only reason I'm writing this out is so that I can see what the equilibrium expression is, the equation. The QSP is equal to the concentration of copper times the concentration of chloride, 1, 1, 1, 1. Because this is an MX, and I'm not using the solubility equation for MX, I'm just saying because it's an MX, I'm going to have copper to chloride both to the exponent 1. Now we can just substitute it in and get the number and see what we get. If you can see that this is going to be the equation directly from that solid, you don't need to write that equilibrium expression down. This is going to be 4.1 times 10 to the minus 4, and it's going to be squared, but I'll write it again, 4.1 times 10 to the minus 4, and what am I getting there? It's going to be times 10 to the minus 8. It's going to be a 16 in there, maybe minus 7. Yeah, what do you got there, Ben? Times 10 to the negative 7, and that is a QSP. Now notice we've got two significant digits here, right? So let's round this because it becomes important or significant. 10 to the minus 7, and we're going to compare that to the KSP, and what do we find? How does the value compare? They're the same. Excellent. So QSP equals KSP. Therefore, how do we describe this solution? It's a saturated solution. Saturated. And will it precipitate form? No, you're not going to see a precipitate form. No precipitate. No precipitate. Now again, that's the easiest of the easy. It's introducing you to the fact that we need the copper ions and the chloride ions so that we can find the QSP. Now we're going to make it look a little harder to find those ions in order to solve the problem. So in a more realistic situation, we have 250 milliliters of a lead 2 nitrate reacted with 450 milliliters of a sodium sulfate solution. And then I give you a KSP for lead 2 sulfate. Now, if I'm really mean, and maybe some university courses would be, they wouldn't give you the KSP, they'd just give you a table. And they'd make you figure out which one we should be calculating for. What we're essentially doing is a double displacement reaction, and we've got to figure out which one is going to be the one that will most likely form a precipitate. Without writing it down, what are the products of my double displacement reaction going to be for those two when they trade partners? What are the products going to be when they swap? Guess what do you got? Right, and sodium as well, right? Remember, sodium is all aqueous and nitrate is all aqueous. So sodium nitrate is one, and it's not going to be those. That's not good. They're all soluble, very, very soluble. Its K would be big. We don't even bother looking. I don't even know where to find a K for sodium nitrate. It's so soluble. So it's got to be the other one. You'd go to then your table and you'd find the KSP for lead sulfate. Now, because I'm not mean and you're just learning how to do this, you're going to have the biggest hint ever. In the question, I'm going to give you the KSP of the ions that we're going to be worrying about. You don't even have to think about the double displacement reaction. It'd be nice if you did, because that's the way you actually do it. So I'm going to need the lead ions and the sulfate ions after dilution. All right? So again, I like to draw a little picture when I'm doing the dilution situation, just to gather all of my information up. I have 250 milliliters, and this is 1.6 times 10 to the minus 4 moles per liter, and this is PbNO3 and brackets 2. And on this side, and I should have wrote it maybe in another spot, but I'll write it down here, 450 milliliters, and this is 2.3 times 10 to the minus 4 moles per liter. And this is Na2SO4. And we are going to dump that into one container, which means I'm going to have a final volume. What's that final volume going to be? Yep, 700 milliliters. And what I need to do is I need to figure out the concentration of the lead in there. And I need to find the concentration of the sulfate, that's plus 2, minus 2, in there. That's what I have to do. What type of a calculation do we call it when we mix, when we change the volume of a solution and we got to find the new concentration? What do we have to do here? I don't need a numerical value. I just want the name to go with it. Jess, what are we doing? Yeah, we're doing a dilution equation, but I'm going to make it a little easier. You're right. C1V1 equals C2V2 is correct. C1 times V1 equals C2 times V2. That's our dilution equation. But what I'm going to introduce you to, because we're not looking for V's and because we're not looking for C1, for this purpose, when we mix solutions or when we, mix two solutions together in some way, we're always looking for a C2. We're always looking for the final concentration. And when you're looking for the C2, you're always going to have this scenario, V1 over V2. Now, V1 over V2 is what I want to change in name to something called a dilution factor. Let's create a new conversion factor, which is simply a dilution conversion factor. If the volume gets bigger, what must happen to the concentration? It gets smaller. If the volume gets bigger, the concentration has to get smaller. So here's the easy calculation. My original concentration, 1.6 times 10 to the negative 4 moles per liter. I'm now going to create a dilution conversion factor that is essentially a fraction that has the original volume over the final volume, with the final volume, when you're dumping it together, being larger, which means the number on the bottom, 250 milliliters over 700 milliliters. The one on the bottom being larger, thus diluting it. So your first step in figuring out your concentration of your ions is the dilution factor. Technically, we need one more conversion factor for this, and I'm going to introduce it to you. It's not something new, but because I'm starting with lead-2 nitrate, I need the conversion factor that tells me how many leads are in each lead-2 nitrate. That, in fact, I believe was one of the first conversion factors I showed you back in grade 11. In other words, I'm simply looking for one lead for each lead nitrate, because if it was 2, I'd need to double everything, right? So this conversion factor looks like this: 1 Pb plus 2 for every 1 PbNO3 brackets 2. And I'm totally out of room here. Same going to be for the sulfate, 2.3 times 10 to the negative 4 moles per liter. I'm running out of room, so I'm not going to write it down. What's my dilution factor going to look like for this one? Christian? 450 milliliters over 700 milliliters. Notice I'm working in milliliters, right? Notice I'm working in milliliters instead of liters. But because they cancel out, it doesn't matter. It has no effect. The milliliters and the milliliters cancel out, and so this just turns into a numerical dilution factor. How much smaller is the concentration getting? And how many sulfates are in each sodium sulfate? Elena? 1. So this is kind of silly, the last one, but it is going to become important. 1 SO4 minus 2 for every Na2SO4. So when we mix two solutions together, and we will be even in the next unit when we're talking about mixing acids and bases, we're going to be doing the same calculations. Don't get hung up necessarily on C1V1 equals C2V2. Think of a dilution factor. We're just diluting it. Big number on the bottom, little number on the top. What are those values, just so that I can write them down here. I'm totally out of space, but yeah, what do you got, Shauna? Times 10 to the negative 5 moles per liter. And do you have the other one yet, or 1.5 times 10 to the negative 4 moles per liter. All we've done is figure out what our concentrations are. Now we're ready to write the equilibrium expression, the trial, the QSP, and compare. Please don't let this be a big job. I want you to, think of that as being a secondary quick thing. Mixing two solutions, oh yeah, I got to dilute it, and I got to figure out how many ions are in each. Boom. Don't dwell on it. So now, I don't think we need to write this out. It's 1 and 1, so QSP is going to be equal to the concentration of the Pb plus 2 times the concentration of the SO4 minus 2. You could have wrote out an equilibrium equation if you wanted to, but it's not needed. 5.7 times 10 to the minus 5. 1.5 times 10 to the minus 4. We're into the 10 to the minus 9 range with then a 5 times almost 2, so 10 to the minus 8, maybe, something like that. What do we got? Ben, what do you got? 10 to the negative 9? 10 to the negative 9? Do we like that? Oh, okay. I thought maybe that was going to get me into the hundreds, but it didn't. 10 to the negative 9. And that's just a Q, so there's no units to it. Let's go back and check. How are we doing? The Q is too small? Q is too small, right? QSP. Are we not liking that number? What do we got for murmuring going on back there? We like it? So what are we murmuring about? Are we murmuring for what reason? Anything? Oh. What did you get? 9.0 times 10 to the negative 9. What did you guys get? 9.0? 8.4? What's 5.7 times 1.5? 8.55. So maybe we're just dealing with a rounding scenario. If we had kept an extra digit here, did you keep extra digits?
I did.
Like you used an answer feature, you used the extra digits, what did you get? 8.44. And who got the 9.0? Did you put in those numbers? So if you do 5.7 times 1.5, you get 9 point something? Yeah, don't worry about it. It's a rounding scenario, all right? It's just a rounding issue. It probably gets us to like 8.4 something something, which then is rounding up somewhere else. Let's not stress over that at this point, because I think at this point we can see that the minus 9 is going to be smaller than the minus 8 anyway, right? So let's not worry about that. QSP is less than the KSP. How would you describe this solution concerning lead sulfate? How would you describe this solution? Yep. It's unsaturated. It's unsaturated. Therefore, no precipitate. No precipitate. Okay? Yeah, that's a significant digit situation. Don't stress over it. All right, let's do another one. This is a different take on the problem. You don't have that one? Oh yeah, it's built into the question. Yeah, I guess that's right. I haven't changed it in an entire year. That's sad. If you look at the very end of the question, it actually looks like it's in the middle. There's a number 3 there. You see it? And it didn't get entered and moved down. So it's hidden in there. It's the hidden question. So it is there. And then I just photocopy it and don't ever fix it. Never fix it. So this one's a little different. The main difference is that we're imagining that we're just adding straight up moles to a solution. So we have 1.25 liters of solution, and we're just dumping in, it might even be a solid, 0.100 moles of calcium chloride. It's not moles per liter, we've just dumped it in, moles, solid. Like we're going to have it dissolve, and then we're going to see whether it forms a precipitate or not. And this solution in here is 0.040 moles per liter, and that is Al2SO43. Oh, and look at, identify the precipitate. That's fun. Which means we need some KSP values. So we need our textbook. Oh, wait a minute. In the question, do I give it to you? Oh, I give you calcium sulfate as it. I was nice to you guys. See at the very back of your question? I give you the KSP. KSP equals 7.1 times 10 to the minus 5. And what's that the KSP of? CaSO4. Too nice to you. No, actually, that's the way we'll do that. We would have had to have gone to some tables and see what it was. So what do I need to find? Concentration of which ions? Yep. Yes, but to put it into the QSP, I first need the concentration of the calcium first, and then the SO4 second. I need those separate, so I can put it into the QSP. But you're right, that's the solvent. Concentration of calcium plus 2, concentration of SO4 minus 2. Now we have to think. I've dumped 1.1 moles in 1.25 liters. What am I going to do? Somebody tell me what to write down. How am I calculating this? I need a concentration. And this is where we put equations out of our minds and we think very logically. How am I going to get my concentration unit out of that information? Catherine, what are we doing? It isn't, but that's okay. Keep telling me how to calculate it. 1.25, right? Liters. And I should technically turn the calcium chloride into just calcium ions. What's my conversion factor to just get the calcium ions out of it? And this is, again, a very simple thing. It's not complicated. What do you got? 1 to 1, right? 1 calcium to 1 calcium chloride. Oops, it's supposed to be equals. Equals. So in this case, I gave you moles, you had liters, no big deal. Figure out moles per liter. Don't even worry about thinking about that equation I told you to memorize last year. Just do it. I'll take that number before we figure out the next equation. Jess, what do you got? 0.0, sorry. And we would like to 2800, like it's right on the money. 0.800 moles per liter. What am I doing here? How am I going to get the sulfate ions? Yeah, what do you got? 0.04 times, sorry? No, it's not 1 over 1, but you're right. We've already got the concentration, moles per liter, but I need the sulfates out of the aluminum sulfate. 3 over 1. 3SO4 minus 2 for every 1 aluminum, 2SO4, 3. It wasn't diluted. It's just the concentration. And there's 3 sulfates in each one. So what is that, 0.12? 0.12 moles per liter. Once you've got the 2 ions, put it in the Q, compare it to the K, and away you go. QSP. And that's equal to the concentration of the calcium and the sulfate. Again, it's 1 to 1. The calcium, 0.0800, 0.120. You'd think I could do that in my head, but I can't. 9.6 times 10 to the negative 3. And that's just a Q, no units. And I don't have it. Oh, here it is. No. The QSP is, we're able to compare size. Yeah, Christian? Yeah, it's greater than the KSP. Therefore, there's too many ions in existence in that solution. Therefore, we're not even going to call it supersaturated because we're going to assume that doesn't set up. It could potentially do that, but we're going to assume then what happens? Yeah, precipitate forms. Yes, precipitate. Okay? Oh yeah, and I've got more examples, as you can see on the page. I'm going to do the precipitate just forms examples as well. All right? And what will precipitate first? We're not doing that. You can actually just cross that off where it says, what will precipitate first? I'm not doing that question. That's one that I sometimes do if I get to it, but we're not doing that one. Okay, so that's how you determine if a precipitate will form, and there's a handful of questions that go with that out of the textbook. But on the same vein, or on the same idea, there are many questions that ask you to do some calculations where the question asks or states, a precipitate just starts to form, okay? And then they're asking, what are the concentrations of? And that's another scenario that we can deal with. So in the previous ones, we were mixing two things together, and we were asking the question, will a precipitate form? And so we find the Q and we compare it. In these questions, an analytical technique to determine the concentration of certain ions can be done by taking a solution with a known concentration of ions and very slowly adding another solution to it. At some point in time, after you've added enough ions, you will create a saturated solution, and then in the very next drop, you will have a precipitate present itself. We can use this analytical technique of just forming a precipitate to determine concentrations of ions that are not known in other solutions. So we take a known solution and an unknown solution, and we slowly mix them until a precipitate just starts to form, and then we stop and we measure the volumes, and we ask the question then, what's the concentration of that unknown? So a precipitate just starts to form when 125 milliliters of 2.5 times 10 to the 8 iron 2 is added to 170 milliliters of 9.9 times 10 to the minus 11, and then some kind of M, some kind of metal. It doesn't matter what it is. And then it's got the sulfate. Oh, sorry, no, that's not M. That's not a metal. That's molar. That's molar. Sulfide ions. And the question is, calculate the KSP. So when we're doing a situation where it's saying a precipitate just starts to form, we're going to assume a saturated solution. And I need to put an E on the end of that. So when the question says a precipitate just starts to form, assume a saturated solution. Even though one drop pushed us over the edge so that we could see the precipitate form, we're going to assume that we've got just enough. That last drop didn't really count. And if we're going to assume a saturated solution, then we can go straight to the KSP. Because if it's a saturated solution, what's true about the QSP? Yep, it's equal to the KSP. So in other words, what we're being told here when we assume the saturated solution, at equilibrium. In other words, we've just artificially, by slowly adding, created a perfect equilibrium situation for a solubility situation. So these calculations really are not too bad. If we're looking for the KSP for FES, then I need the concentration of Fe plus 2, and I need the concentration of S minus 2, and I put them in and I get the number. And that's really the way we calculate KSPs. So we can do that calculation. So let's come up with our ions. We're obviously doing some dilution here, and I'm going to run out of room. Concentration of Fe2 plus. I didn't draw the picture, but I have 2.5 times 10 to the minus 8 molar, and I've diluted it. What am I putting into that dilution factor? Because I've poured them together. What's my dilution factor looking like? What's the dilution equation? Yeah, Christian? 125 milliliters over, is that 500? Is that what you said? Or 300? Did you say 300? Oh, that's all right. Is it 300? Over 300. 300 milliliters. Less gaming, Christian. And the same with the S2 minus. 9.9 times 10 to the minus 11. And here we've got the 175 milliliters over 300 milliliters. That little dilution factor is going to come into play quite a bit. But it's nothing to stress over. It comes from C1V1 equals C2V2, but we just do that. Now we're just going to do it. We're not even going to think about it. And I'll just write it straight into my KSP. You guys have it written down here, obviously. What is the iron concentration after that dilution? Mallory, what do you got there? Got numbers? You can give them to me to 3, and then we'll round back. Did you keep 3? Yeah, I'll keep 3. Yep. Times 10 to the negative 8. And the next one? Yep. Negative 6. And put them together. And then you can round back to your 2. It's good practice. Keep an extra one through your calculations and then round back. We're not liking something? We do like it? We don't like it? We don't like that? 5.77 times 10 to the negative 11. Mallory's never going to give an answer again. 5.7. 5.78. Oh, not there. What am I doing? 9.9. Is it over here? 5.78? 7, 8. All right. And then I'll round it back to 2. I won't ask Mallory. So I'll ask Shauna. So I'll ask Shauna. What do you have? Ten to the negative, was it a 19, did you say? 10 to the negative 19? How do you get 10 to the negative 19 out of that? Oh, this is a negative 11? Ah, that'll do it. I don't know why I wrote down negative 6. We agree on that? Very straightforward. Again, we've got a dilution. Find your concentrations. Find the KSP. So here's an example that is, like I was describing to you, a technique that can be used to calculate concentrations of unknown ions, especially for things of very low solubility, like mercury chloride. So if you, or this is mercury 1 chloride. So if you took a sample of water, say from the Sydenham, all right, There's no lead, there's no mercury in the Sydenham. I just like making fun of the Sydenham River. It used to be funnier because Alvinston used to draw water from the Sydenham River. How many Alvinstonians am I offending here? None? Nobody from Alvinston? So that's no fun. I need another river somewhere else that people are drawing water from. No, I got nothing. St. Clair River. Who knows? Okay, there's no mercury in the St. Clair River either. But anyway, if you drew a sample of water and you wanted to test it, you could use this particular technique. So we're looking for mercury ions, and what we do is you have a solution that contains chloride ions, and then you slowly add that mercury, and then you eventually get a precipitate to form. You stop right when that precipitate forms. To test for mercury contamination, chloride ions are added to form a precipitate of HgCl if the chloride ion concentration in the sample is. So in other words, if we know what that chloride ion concentration is, 5.3 times 10 to the minus 2 moles per liter. The question is, calculate the maximum concentration of the mercury ions in moles per liter in that sample. So we've got Hg plus, and that's what we want to find. And they give us the KSP. In this case, we didn't make you do any dilutions or anything like that, but essentially what I'm saying is this is a very straightforward, write out your KSP expression, you've got the KSP, you've got the chloride ions, rearrange and solve for the mercury ions. So this is a very straightforward example, a very simple one. KSP, concentration of Hg plus and Cl minus. Again, I've only been dealing with ones that are 1-to-1. If we had a 2 there, right, 2 chlorides, we'd need a squared. This is very straightforward. And so 3, oops, I'm putting in the wrong spot, getting my numbers in the wrong spot. 1.5 times 10 to the minus 18 equals, and I'm looking for the Hg plus, and I know 5.3 times 10 to the minus 2, and I'm solving for the Hg. And I'm not even going to rearrange that. You guys can do that, Hg plus. Yeah, Christian, what do you got? Negative 17. We're on fire today, aren't we? Moles per liter. We'll get there. Again, a very simple example, but again, when it says in the question, a precipitate just starts to form, it means you can use that KSP expression straight up and just solve for what it's asking you for, all right? If it's, again, to differentiate between earlier today, if it says, will a precipitate form, you're solving for Q and comparing it. Here where it says, a precipitate just starts to form, or to form a precipitate, you're assuming it's saturated and it's at equilibrium. One more. This one also seems to be very straightforward. We're not diluting or anything. What concentration of Br minus 1 must be present to just start the precipitation of lead 2 bromide from a 3.0 times 10 to the minus 2 molar solution of lead 2 nitrate? In this case, again, I'm going to be using the expression for PbBr2. I'm wanting to find the bromide ion concentration, Br minus, question mark. I need the lead concentration, Pb, and this is plus 2, square brackets, and 3.0 times 10 to the minus 2 moles per liter. And that's of lead nitrate, so again, it's 1-to-1, right? We've got that 1-to-1 ratio, 1 lead to 1 nitrate. 3.0 times 10 to the minus 2 moles per liter. So again, because we were given lead nitrate, we had to separate it out. Those are little tricks that we can throw in there. You got to pull those ions out if I don't just give you the straight up ions. This again is a very straightforward one, KSP. Oh, I got to be careful here with this one. It's PB plus 2, and it's BR minus 1, but because there's 2 bromides, that's going to be a squared, right? Because we're going to have the 2 when we separate it out. So that one has a squared in it, which means eventually we're going to need a square root. Are you frowning because of this number 2? No?
Like would you have to divide by 2 on
No, because look at where this lead is coming from. This lead is coming from this lead nitrate, all right? And what this statement says is there's 1 PB plus 2 in each PbNO3 brackets 2. What I'm doing in this equation is I'm pulling out the leads out of the lead nitrate solution. And this 2 really has nothing to do with my lead concentration because the lead is originating from the lead nitrate that's in the solution. Okay? And this 2 really only tells us that it's going to be a squared when it falls apart. All right? So what do we got? We've got 6.6 times 10 to the minus 6. That's equal to, now I've got my lead value, 3.0 times 10 to the minus 2, and that's equal to the concentration of Br minus 1 all squared. We need to divide it off and take the square root. 6.6 times 10 to the minus 6 over 3.0 times 10 to the minus 2. That's Br minus 1, and that's all squared. So we're going to take the square root of that thing. And approximately 6 minus 6 minus 2, that's minus 4. Take the square root, that gets us to about minus 2. Somewhere in the minus 2 range. Could be minus 3. What do we got? Catherine's looking at a number back there. What do you got? Negative 2. 1.5 times 10 to the negative 2. We like it? 1.5 times 10 to the negative 2. It's a concentration, moles per liter. Okay? Moles per liter. Okay. And I'm not going to do the which will precipitate first. That's actually a neat technique. You could actually have a mixture of ions, 2 ions that are not very soluble, like maybe 2 anions like lead and mercury. And if you slowly add chloride, you could actually get one of them to precipitate first and use that technique to separate out various types of ions from a solution. That's a little more complicated, and I want to give you some time to work on these. So that's that. So we're not doing that one there. And in terms of the homework for this stuff, that big long sheet that I gave you the other day, the second section is on a precipitate just starts to form or will a precipitate form. So those questions in that second section of that long sheet, you can do that as well. Okay? Also a reminder on that long sheet, ignore the textbook questions that are assigned because that's the old book. Tomorrow's common ion effect. And then that's the last one before our test on Monday.